Hello everyone, it's a lovely morning, and what better way to start a Saturday than with some advent of code. So, let's do some programming. For those just tuning in, we're solving advent of code. This is a programming competition of sorts that runs between 1st and 25th of December. There's one problem a day, and each problem has two parts, although you can only see the second part after solving the first. Advent of code is kind of nice in that it has a gradually increasing difficulty curve. As in, the first few exercises are very simple, and then they get harder and harder and harder. So, lots of people use this as an opportunity to learn something new, try programming in a way they haven't before. For me, I'm trying to stream it and also to solve it in Elixir Livebook. Speaking of which, we're solving these in Elixir Livebook. This is a web app. It lets you intersperse text and code, and whenever you write code, Livebook also executes the code underneath. So for example, here's the solution to part 1 from yesterday, and there's a bunch of code, and then a function call, and then the output to that function call. I think this is a pretty good programming environment for trying things out and for solving problems incrementally. It's pretty terrible if you have to have more than one file or if you need structure in your project. But if you're just but for the top level of a project, for the top level of solving a problem, this is pretty great. And then Livebook has fancier features. It doesn't just let you write code and execute it. Some of the code you write can also generate input elements, for example. So here we're generating a text area. Then we can fill in the text, and then we can later read it. And whilst I didn't do this on stream, I realized that yesterday was a perfect opportunity to show something else, to show off one other of Livebook's capabilities. So here, for example, we're generating a graph. Because Livebook can just do that. We're taking the input and then we're reading it, generating a textual description for a mermaid chart, and then we just pipe it into Kino Shorts Mermaid, and this generates the graph. So this was the first example, and here was the second example, and third. And this would have actually been a pretty nice way of exploring the problem space yesterday. I didn't do this, I just thought about it manually. So, lessons going forward. Use more of Livebook's features, because Livebook is pretty good at this. Alright. Now back to Advent of Code. Let's actually see what's in store for us. Now, perhaps I should mention, the story arc for this year is that we're trying to save Christmas by fixing the snow machine. I don't think things are looking good because we haven't actually taken any steps towards fixing the said snow machine. We've done basically everything other than that. Most days we just play some games with elves. Like here we played, on day 2 we played a game with puzzle blocks with elves. On day 4 or 5 we computed scratch card winnings. One of these days was a submarine race where the submarine could only move forward a few millimeters. And then 2 days ago we played poker with an elf ghost. Yeah, we've done basically everything other than fix the snow machine. But hopefully we're getting closer to the mountain range where we can fix the sand which we need in order to filter the water for the snow machine. So, let's see what today is all about. Day 9. Mirage Maintenance. You ride a camel through the sandstorm and stop where the ghost maps told you to stop. The sandstorm subsequently subsides, somehow seeing you standing at an oasis. The camel goes to get some water and you stretch your neck. As you look up, you discover what must be yet another giant floating island. This one made of metal. This must be where the parts to fix the sand machine come from. Oh, right. And we're traveling across an archipelago of floating islands, which is kind of like One Piece, but with a lot less piracy and adventure, and just many, many more games. There's even a hang glider partially buried in the sand here. Once the sun rises and heats up the sand, you might be able to use the glider and the hot air to get all the way up to the metal island. While you wait for the sun to rise, you admire the oasis hidden here in the middle of Desert Island. It must have a delicate ecosystem. You might as well take some ecological readings while you wait. Maybe you can report any environmental instabilities you find to someone to the oasis so the oasis can be around for the next sandstorm-worn traveler. You pull out your handy oasis and stand instability sensor. I guess we were secretly geologists all along. So you pull out your handy oasis and sand instability sensor and analyze your surroundings. The oasis produces a report of many values and how they are changing over time, your puzzle input. Each line in the report contains the history of a single value. For example, to best protect the oasis, your environmental report should include a prediction of the next value in each history. So each line is a history and we have to predict the next value. To do this, start by making a new sequence from the difference at each step of your history. Start by making a new sequence from the difference at each step of your history. If that sequence is not all zeros, repeat this process using the sequence you just generated as the input sequence. So every time we do this, we'll have one less value. Once all of the values in your latest sequence are zeros, you can extrapolate what the next value of the original history should be. In the above dataset, the first history is 0369, so 3. The first history is 0369, 12, 15. So this is the input. Because the values increase by 3 at each step, the first sequence of differences that you generate will be 33333. Yes. Note that the sequence has one fewer value than the input sequence because at each step it considers two numbers from the input. Since these values aren't all zero, repeat the process. The values differ by 0 at each step, so the next sequence is 4 zeros. This means you have enough information to extrapolate the history. Visually, these sequences can be arranged like this. Yep. To extrapolate, start by adding a new 0 to the end of your list of zeros, because the 0 represents differences between the two values above them. This also means that there is now a placeholder in every sequence above it. To start by filling in, you can start by filling in the placeholders from the bottom up. A needs to be the result of increasing 3, the value on its left, by 0, the value on below it. This means that A must be 3. Finally, you can fill in B, which needs to be the result of increasing 15, the value on its left, by 3, the value below it, or 18. So the next value in the first history is 18. Finding all 0 differences for the second history requires an additional sequence. Right, so we start with 1, 3, 6, and so on. So the second sequence is 2, 3, 4, 5, 6, then 1, 1, 1, then 0, 0, 0. Then following the same process as above, work out the next value in each sequence from the bottom up. So the next value in the bottom sequence is always 0. Then we take a 1 and add 0 to it to get a 1. Then we take the 6 and add a 1 to it to get a 7. Then we take 21, add 7 to get 28. I wondered if this is some form of derivation. No, differentiation. It feels a lot like we're doing multiple levels of differentiation. So the next value of the second history is 28. The third value requires even more sequences, but its next value can be found the same way. I wonder if we're guaranteed to always end with a sequence of zeros. So the next value of the third history is 68. if you find the next value of each history in this example and add them together, you get 114. So 114 is 68 plus 28, that's 1896, 104, 124, 114. Yes. Analyze your OASIS report and extrapolate the next value for each history. What is the sum of these extrapolated values? Okay. This is almost certainly just doable. Right, look at it. How many? So let's look at the full input for a bit. We do not have that many sequences. There's definitely less than 100 sequences here. And then each sequence has less than 100 elements. And the way this algorithm works means that it will be quadratic in the length of the sequence, because we'll have to do one step. If we just follow the algorithm and don't do anything clever, we're just going to go through all of the elements once, then go through through n-1 elements, then n-2 elements, and so on, and then work our way back up. So following the algorithm will be quadratic in the length of each sequence, and then we'll have to do this once for each sequence, and there aren't that many sequences. Yeah, so the plan is we're just going to code up the algorithm they described. And I assume part 2 will be trickier, but we'll solve that when we get to it. So let's get going. We're doing this in Livebook, and we start with a new notebook. This is going to be called AoC 2023, day 9. Let's now save this to make sure we don't lose it if Livebook crashes. It hasn't actually crashed so far, but better safe than sorry. We're going to need Kino as an input, because we are going to need Kino as a dependency, because we want to use the Kino inputs to read our input. First section is going to be called helpers. Now we're just going to do example. One is Kino input text area. And this generates a text area where we can plop our input in. And we're going to need the second one of these for the full input. Let's copy the example and the full input in so that we don't have to worry about this later. Here we go. Also notice that there are some negative numbers in the full input. Well, we'll deal with this when we get to it. Block. So, solving part 1. We create a new section and start by reading the input. Now we have the input as a strings where the lines are separated by new line characters. So string split on new line. Now we have a list where each line is an element. And we also have an empty string at the end because our input had a trailing new line. We could fix the input, but let's just solve it programmatically so that we don't have to worry about this later. Okay, now we have one line per input. Next, we're going to parse these as integers since we're going to have to do arithmetic on them. So enum.map, we do something for each line. And then thing we do is we take line, we pass it through string split on space. Now we get, for each line, we get a list of strings. And then this we pipe into enum map string to integer of 1. And here I'm using the Elixir syntax for referring to a specific function of a given array. In this case, string to integer, which takes 1 argument. So now we have, for each input line, we have the actual numbers as integers. So the next step is we have to actually follow the algorithm and predict the next value. we're going to do this in a separate function because, yeah, it will have to be some sort of recursive thing. We could probably do it with an enum reduce until, but it will be more clear as a recursive function. So again, for each input line, we're going to call a new map, and then we're just going to call, let's say, part1 next value, which takes a single argument as a parameter. And this, of course, doesn't compile because we don't have a part1 next value. But that's what we're going to do now. We're going to define first a module. We have to put this in a module because Elixir doesn't like top-level functions. Then we're going to do a next value. Let's call these x's. When is list of x's? Let's just return x's for now to see that it works. It does work. Okay, so step one in our algorithm is to compute these following sequences of differences between elements. And the way we're going to do this is, again, recursively. Is it recursively? So the thing we really want to do here is, what do we want? Let's say predict, let's call predict x's. And we're hoping predict x's returns the only thing we need. So we're at the top level. Then we want to call a function that generates this, but really all we need to return is the a from underneath it. So when we're at this level, we call a function that generates the subsequence and returns the last digit. So predict sub last digit. Sub last digit is this. And then we return, we append a new value. First we take, then we return x's, so our input list with list.last of x's, so the last value in x's, to which we add sub last digit. And I bet we'll be able to merge predict sub last digit and next value. We'll be able to merge them in the same function. But for now, let's just call them different. Let's just have different functions. Predict sub last digit. X's when is list of x's do, and this has to do something. Let's return 0 for now. Now, the base case for predict sub last digit is when we have a list of only zeros. When we have a list of only zeros, we always return a 0. So if list, probably called enum.all, if enum.all of x's, and then if every element in the list is zeros, then we return a 0. Otherwise, we have to, so if all of the elements are 0, we return a 0. But if they weren't 0, then we have to call sub last digit, predict sub last digit again, and then do the addition to create new last digit. Then basically have to call this. So first we generate the sublast digit from the sublist, and then we add it as the last digit. Or rather, we don't add it, we just return it. And I'm realizing here that we failed to do the subtraction at some point. There needs to be, we need to subtract elements, we need to subtract pairs of elements at some point. Probably here and here, right before calling predict sublast digit, we have to do some extra processing. So let's create a new section. Let's call this experiments. We're going to branch this off of helpers so that it doesn't so that we don't have to execute part 1 in order to execute experiments. And then here we're going to write 3, 6, 9, 12, 15. This was basically the first example. Now, how do we compute the next sequence? The sequence, how do we do the differentiation step? I think we do enum chunk by 2, chunk by 1, expected a function, chunk every 2. Okay, so this gives us 3, 6, then presumably 9, 12, written as a char list because Elixir thought that these looked like printable characters, and then 15. Now, we want step 1. Okay, this is what we want. We want 3, 6, then 6, 9, then 9, 12, then 12, 15, and then 15. Okay, and what was left over? Can I see? Let's see the documentation for this. Chunk every. I want to see what leftover is. If discard is given to leftover, the last chunk is discarded unless it has exactly count elements, which is exactly what we want. We don't want just a single 15 here. So discard, is this what it meant? Yes. Okay, now we have pairs of elements in the list. So next up we do what? We do an enum map, and then each thing will be 2 numbers, a and b, and we're just going to return b minus a. Now we have the subsequence. So this is what we want. So let's put this in a new function. Let's call it diffs. And it takes an x's when is list of x's. And then, yeah. Then we copy the code that we figured out below. And this gives us now the list of diffs. So here, next value, when we call predict last digit, we are actually going to call this on diffs. And here, when we call predict sub last digit again, we're again going to do it on diffs of x's. So this should work, although it might crash violently. It outputted something, so 0, 3, 6, and 18. Is 18 correct? 18 is correct. The next one is going to be 28. Then 28, and then 68. 68. Alright, so this actually worked. But before we actually submit the answer, this looks horrible. Like, this is clearly unnecessarily clunky. And I think we just don't need next value, do we? Yeah. Really, we can just call this next value. And now this is just going to show the last value in each list instead of the whole list, which is kind of what we need. Now here we just do enum.sum 114. Because we need the sum, and it is indeed 114 for the example input. Does this also work for the full input? Oh, that's a large number. That's the right answer. You are 1 gold star closer to restoring snow operations. Okay, so we just followed the algorithm and that was enough for part 1. Let's do part 2. Let's see what part 2 is all about. Of course, it would be nice to have even more history included in your report, should itself to just extrapolate backwards as well, right? For each history, repeat the process of finding differences until the sequence of differences is entirely zero. Then, rather than adding a zero to the end and filling in the next values of each previous sequence, you should instead add a zero to the beginning of your sequence of zeros, then fill in new first values for each of the previous sequences. In particular, here is what the third history looks like when you extrapolate back in time. So we start with 1013, right? This is 1013 is 1013 through 45 is our third example. So 1013 45. Then we do the normal differentiation, then another one, and then we end up with zeros. And then it says add a zero at the beginning, then extrapolate back. So this is 2 minus 0 is 2. 0 minus 2 is minus 2. 3 minus minus 2 is 3 plus 2, which is 5. And 5 minus 5 is 5. Now, I can make this text a bit bigger, can't I? Yes. I made the text bigger because, well, I have lots of screen space available. Right. Back to the problem. Adding the new values on the left side of each sequence from bottom to top eventually reveals the new leftmost history value 5. Doing this for the remaining example data above results in previous values of -3, 0, -3 and 0 for the first and second history. Adding all three new values together produces 2. Analyze your OASIS report again, this time extrapolating the previous value for each history. What is the sum of these extrapolated values? This is suspiciously easy because let's just try writing it and see if there's some clever thing we're missing here. So, part 2. I find it's much easier to reason about things when you actually try doing them. So let's just copy part 1 for starters. We switch back to looking at the example, which is called example 1, and then we get the answer for part 1. We don't sum up anymore so that we see what's going on. So this is part 1 next value. Let's now instead do part 2 next value, which is going to be very similar to part 1, I suspect. Def next value x is when is list x is. I don't actually need to write this guard here to check that the input is a list. I just like writing the guards whenever possible because it's very easy to pass the wrong value in Elixir, especially when you're doing something in a pipeline like this. So it's really nice to get the runtime to just error out early and tell you that you passed the wrong value to a function, rather than risk it doing something unexpected and then wasting time debugging that. Okay, part 1 next value. So it starts off the same as with part 2. If num.all x's, if all of the numbers are 0, then the first value has to be 0, right? Indeed, if all of the numbers are 0, then the first value is 0. Oh, in fact, this is not called next value anymore. This is called prev value. And here we're just going to be calling prev value. Okay, back to here. So what happens if all the numbers are not 0? If all the numbers are not 0, we call prev value on the diffs. So we call this on the sub list, and then list dot first of x's minus pre-value, right? So when we're at this step, we first call diffs to generate 0, 0. Then we call pref value on that to generate the extra 0. And then we compute the first element minus the pref value from the subsequence to get our own previous value. So this should be it. Undefined function diffs, right? It's called part 1 diffs. So we get minus 3, 0, and 5. This doesn't sound right. Oh, 5? Oh no, it is. Minus 3 and 0. Analyze your rheosis. What is the sum of these extrapolated values? So we uncomment the sum here. This gives us 2. This is 2. Whoa. 1072. Well, this is anticlimactic. That's the right answer. You are 1 gold star closer to restoring snow operations. So yesterday was actually a tricky problem because we had to spot that the graphs were cyclical, and then we had to realize that we have to compute the lowest common multiple of some numbers, which turned out to be prime, so we could have done some extra optimization. Today was just follow the algorithm again. A bit disappointing. Why is this conceivably harder than yesterday's? Presumably because some people don't know how to use recursion, so this is a lot harder if you have to do it iteratively. This would have been trickier to do if you couldn't just do a recursive call like this, I guess. But even generating the new lists would not have been hard. Even doing this in C would not have been particularly hard if you were willing to just modify the lists and then modify the lists on the way down and then modify them back on the way up. Having part 2 be generate elements at the beginning instead of at the end makes me think that the difficulty here was if you store these as arrays and then you had to shift the arrays one element to the right in order to make room for the first element. Yeah, okay. I don't know. I don't know why why part 2 was supposed to be harder. Okay, back to our code. What can we share? We can refactor this a bit and move the parsing to a common module. We're going to put this in our helpers section, and this is going to be called AoC. It's def read input. This takes as an argument a Kino input data structure. Then we put our parsing code here. We indent this. The input is now called input instead of full. Does this compile? It does. So here, instead of doing this whole thing, we just do the AoC read input full. And the output, the result shouldn't change. Yep, let's do the same here as well. And again, the result shouldn't change. It has not changed. We don't really need the experiments, but we don't have to delete it either. how are the stats looking like today? So about a fifth of people still haven't actually solved part 2 from yesterday, which is unsurprising because, again, that was actually tricky. By comparison, everybody who's solving part 1 today is also going to be solving part 2. Like, this is the number of people who have only solved part 1. Yeah, basically everybody is going to do both parts today. Okay, well, thank you for tuning in. This was less exciting than I had hoped. But maybe tomorrow is going to be a more interesting problem, a problem that actually makes us think. So thanks for watching, and bye-bye. See you tomorrow.